Okay, so this is the second half of the projectile motion notes where we're dealing with the angle greater than 0. So there is a slight difference with these problems because we're no longer just dealing with the horizontal velocity. Previous problems we had like a ball or maybe an apple launching out straight horizontally or a ball rolling off a cliff, but now we have something being launched at an angle. So we do have that horizontal component of velocity, but we also have the vertical. So we can solve this. We can use two equations from the reference tables, these two. Okay? And these state that, in general, any vector that we treat as a hypotenuse or resultant vector, so these a's here, we can break them into our components. So if we want the horizontal component, for example, denoted here as ax, we take that hypotenuse and times it by the cosine of the angle. If we want the vertical component, we take that and we multiply the hypotenuse by the sine of the angle. And then we translate this or we transfer it to our case. And in this case, we're talking about the velocity in the horizontal and vertical direction. So we have our Vx, which is equal to our initial velocity times the cosine of theta. And then we have our Viy is equal to our initial velocity times the sine of theta. In sixth period, you're going to want to make this change. Yours just says V here. It should say Vi where I just circled. And then we have Vfy, or the final velocity in the y direction, is equal to Vf sine theta. And the same thing, sixth period, you just have V, it should be Vi. We want to make that distinction because it can be different depending on the problem. Okay. Let's look at our variables and see how they are the same and how they changed. So in the vertical direction, we always have acceleration due to gravity. Acceleration due to gravity close to the Earth is negative 9.81. That's a 2. Sure it is. Believe me. Okay. So we have our displacement in the y direction, which is also the same. Okay. And our time. The time will be the same. Okay. Time is scalar. So we then have to change our Vi and Vy. So we have Viy. We just used the equations from the previous stage. Is the sine of theta. And our Vfy. And Vi sine, or Vf, I should say, sorry. Vf sine of theta. So that's our 1, 2, 0, 5. So we use our free fall equations for that. And in the horizontal, we still have Vx, or horizontal displacement range. We have our time. We have our Vx. Okay? So even though we're looking for this cosine, Vi cosine theta, once we find that, once we do the trig, it's still going to be constant. So it's not going to be changing. So it's a constant velocity, just like before. We're having to do a little extra step. So let's do a practice problem. So we'll open up this bad boy. So I've separated out my two components there. So let me draw it out. So we got a football. It's kicked at an angle of 37 degrees. Well, initially it's 37 degrees. And like a boss, okay, so I kick it at 20 meters per second. But that's our velocity here in this hypotenuse. Okay? So we're going to need both the horizontal and the vertical. So we're looking for the maximum height. Okay, so to me, maximum height means maximum height. So where is it at the top of the arc? And we're looking at the top of the arc right here. So that's just the distance from the ground up here. So now we're just dealing with vertical components. Because I just want to know the maximum height. So that's a change from the ground up to the top. So what I'm going to do is I'm going to take the problem over here. I'm going to say, okay, that's our ground. This is our ball. I'm going to redraw it just as that problem. So we're just looking at the vertical component. So we can just treat it as free fall. We know that any object we're dealing with free fall at the maximum height, the velocity is going to be 0 because it's changing direction. So our Vfy is equal to 0 meters per second. We also know acceleration due to gravity in free fall is negative 10.81. They're on Earth, I'm assuming. We'll state that, but let's just assume that people's football. I don't know why football's capitalized. It's kind of weird. Like Wii football. Okay, so where was I going with this? Okay, VFY is 0A. What else do we know? Okay, well, we can figure out the V initial because we have this 20 here. We have the angle here. Okay, so we have VIY is equal to our VI sine of theta. Okay, so that translates to, if we sub in, our initial velocity is at 20 meters per second. What? Let's do it again. Is our 20 meters per second sine of our angle. I'm going to go over a little bit. It's okay because we're not going to use the horizontal part for this. But just imagine I didn't. Okay. This is equal to 12 meters per second. That's my calculation. Okay, so then we are looking for the maximum height. So that's our displacement in the y direction. That's our question mark. I'm on the box again. Oh well. Deal with it. So I'm looking for an equation that has VF, A, VI, and D. So I could memorize it like a dummy. Maybe not like a dummy. But unnecessarily memorize it. Or I could just say, I know where these are in the reference table, and I just have to find an equation that has VF, VI, AD. Okay. If by default the people that memorize it are dummies, that'd be a dummy. But let's be on the side of the point. So, oopsie. What happened? Uh-oh. Major party foul. What? Okay, let's try that again. It's up, it's running. Stuff's going on. Yeah, I know it. Vy squared equals VIY squared plus 2AD. So what? So to get the dy by itself, we're first going to subtract the VIY squared. Squared. So we get VFY squared minus VIY squared. Do we? Does anyone ever notice how sometimes I write the 2's with a line and sometimes I write them with a loop? It's kind of weird. And sometimes I forget to put the marker back where it goes. I should say the eraser. Okay. We'll get there eventually. Okay. So, now we have to get rid of this 2a, so we divide by our 2a. Divide by our 2a. Okay, so I'm going to write on this. I'm just going to move the dy over to the left. So we have VFY squared equals VIY squared over our 2a. Yeah, I don't know why I did it. The whole, sometimes I look 2's and sometimes I write them the other way. Anyways, moving on. So, if I could see it up there, we'd know that our V final is 0. So that's just equal to 0. That should not be an equal sign. But you already knew that. If you were in class, you'd be yelling at me. Okay, there we go. So it's 0 minus our 12 squared over our acceleration due to gravity. That turns out to be, I can't see the page for some reason. That turns out to be 7.3 meters. What we're saying is this height here is 7.3 meters. So that first problem is solved. We got the max height. So for the second problem, I'm going to redraw. Oh, that's amazing. Okay, so if we're going to use these variables here from the last problem, we have to realize that we're only dealing with this first half of the trip because we found the maximum height from the starting point. So that means we're only dealing with this part of the trip. But we want the total time, so we also need the second bit. So if we're going to use this variable, the VFY, remember that's at the top. So that's only half our time. If you think about it, we're going from the start to the finish. Okay. So if we use these parameters, we went from the start to halfway through, so to here, and now we have to add that second half in, so that's why we double the time. And we're going to double the distance. Okay. And we're going in full motion. So if I look at this in terms of just the vertical, I start here, I'm going up here, I'm going back down here. So I'm bringing my ground over, I'm bringing my max height over. So we start up, we go up, we reach the top, we stop for just that minute second. And I stop, I should say we have a zero, the velocity of 0 meters per second, and we start to accelerate downward. Let's double the trip. So this part here, this first part, is going to be our t. But we also need this, which is also going to be equal to t because acceleration due to gravity is constant. So the time it takes to get up to this point is the same amount of time it's going to take to get back down. So if we just double the time, because we're only looking at that first half of the trip, we can get the total. And that's because we're using these parameters of VFY is 0 and VIY is 12. Okay? So I'm going to use, we use a multitude of equations. I am going to use VIY, let's try that again, VFY. VFY equals VIY plus AT. I'm going to use this one because there's no squares, I don't have to deal with 1/2, any of that kind of stuff. And VF is already on the left side. Actually, I'm solving for time. But still, there's no 1/2 per square. So it just makes it easy. We're solving for time, so we're going to subtract the negative VIY. That. Okay. We have VFY minus VIY equals AT. For time, so we divide by our A. Divide by our A. I'm just going to put the T on the other side just because that's how I like to write it. You don't have to. Now we have this equation. Okay. So, sub in. We have 0 meters per second minus our 12. And then we have acceleration due to gravity is negative 9.81. So our time turns out to be 1.22 seconds. Okay? So that's only for half the trip. So now you have to say something along the line of this is only the time for half our trajectory if we want to be all physicsy. Trajectory. Oh, that's 2 E's. Trajectory. Okay, so this is only the time for half the trajectory. So, words I'm having trouble. Getting late, boys and girls. We need to double it. Double the time. Okay. So 2 times 1.22 seconds. And this is rounded, so when we actually do it in the calculator, it actually equals 2.45 seconds. Okay. So our T is equal to 2.45 seconds. You're going to want to box that up all nice for the readings. Okay? So our T is 2.45 seconds, so we have the total time. Alright, that was that problem. A couple more to go. So how far away is it hit? Okay? So we have this bad boy. What we want to know is the horizontal displacement, okay, or the range. So we actually don't even need anything except for the time from this side. There's no longer question mark. It's 2.45 seconds. So we can ignore all that. I wouldn't do that on your paper because I can erase it. You can't. Okay, so 2.45 seconds. Well, you can erase it, but you have to rewrite it. But I don't have to. Okay, moving along. So T equals 2.45 seconds. Yes, that's a 5. Everyone's going to complain because it looks kind of like an S. Anyways, so T is 2.45 seconds. We are looking for Vx. And we can find the Vi. We know that the initial velocity, the hypotenuse, resultant vector is 20 meters per second. And we use our equation, Vx equals Vi cosine of theta. And sub in. And then we find Vx to be 16.0 meters per second. Now we just use our handy dandy equation. Vx equals dx over t. Because in this case, our Vx here, I'll try it again. Oh no, it's a different one. Our Vx here is constant. So we can use that equation. That's the whole problem. So we're solving for time. We multiply through by the time. We get dx equals Vx times the time. And we solve for dx. Sub in our variables. So we got 16 here. Times the time is 2.45. We get a dx is equal to calculation sound, or taking a look at my paper, 39.2 meters. That means from this distance here that it was kicked is 39.2 meters. So the last two problems were conceptual. Well, they're thinking problems. There's not really any math that you really have to do. These would be 1-point problems on the readings. And if you're thinking, you redraw. So at the top, you might be tempted to say that it's 0 meters per second, but it's not asking for the velocity in the y direction. It's asking for the total. So that's the combination of the horizontal and the vertical components. We know at this point, Vy is equal to 0 meters per second. But our Vx, which is constant throughout, is our 16, which we just found. Okay? So that means our total V is also equal to 16 meters per second. It's a combination of the two vectors, or y vector, which is 0. So it still has a velocity of 16 meters per second at that point. Second part, acceleration at the maximum height. Please, come on. So acceleration is never changing in these problems. It's always the same. It's always negative 9.81 meters per second squared. That's a horrible thing. We should know this by now. If you don't, I feel bad for you. So yes, the acceleration at the maximum height is still negative 9.8, and that's why it changes direction, because it's slowing down, and that acceleration is still affecting it, so it changes direction. So we're actually all done with these notes. We don't have to do the last problem, because that's beyond the scope of our class. I realized today when I was making up these notes that when I took physics in high school, I took Gemini. That's why I just realized that's why sometimes I get overdo stuff. I didn't actually need that problem. So the last problem you can just cross out. You can do it if you want to. You don't have to. Okay? So have a good night. Hope this helps. It clears up any mistakes I made. So see it on Monday. We will finish up projectile, do a little review for the test, and have a good weekend.